March 6, 1944, high above the Third Reich. On a cold morning in early March 1944, the skies over central Germany became the stage for an aerial confrontation unlike anything seen before in the European War. At nearly 28,000 feet above Berlin, squadrons of the U.S. Army Air Force's 56th Fighter Group clashed with large numbers of German interceptors in what would later be recognized as the largest fighter engagement of the conflict to that point. What unfolded during that mission stunned both sides. As combat spread across the upper atmosphere, German pilots relied on a tactic that had served them well for over a year. After striking American bomber formations, they would pull sharply upward into near-vertical climbs, trusting that their lighter, more agile fighters, the Focke-Wulf W190 and the Messerschmitt Bf 109, could simply outclimb their pursuers. Against earlier American escorts, this maneuver was almost always successful. But on this day, the rules had quietly changed. American P-47 Thunderbolts did not fall away as expected. Instead, they stayed glued to German aircraft through punishing climbs that should have exceeded their limits. Near the edge of aerodynamic stall, with engines roaring and air thinning, Thunderbolt pilots squeezed their triggers. Cannon and machine gun fire tore into enemy aircraft, sending trails of smoke spiraling downward as German pilots abandoned their machines. By the time the mission ended, the 56th Fighter Group reported 11 confirmed enemy kills without losing a single P-47. This dramatic reversal did not come from new tactics or pilot training. It came from engineering, a problem hidden in plain sight. For much of 1943, American bomber losses over Germany had mounted at an alarming rate. Escort fighters repeatedly reported the same frustration. German aircraft could attack and then escape upward, untouched. The P-47 Thunderbolt, despite its ruggedness and firepower, struggled to climb efficiently when it mattered most. The heart of the problem lay not in the engine, but in what translated engine power into motion. The Thunderbolt was powered by the formidable Pratt & Whitney R2800 double wasp, a radial engine capable of producing around 2,000 horsepower. On paper, it should have delivered exceptional performance. Yet in practice, the aircraft lagged badly in climb rate, especially at high altitudes. Early production P-47 seconds were equipped with narrow-bladed Curtiss electric propellers. These propellers were designed with speed in mind. At cruising velocities above 350 miles per hour, their slim blades sliced through the air efficiently, minimizing drag and maximizing forward momentum. Climbing, however, is a different aerodynamic problem. At lower airspeeds and high engine power, an aircraft needs a propeller with enough blade surface to grab dense air and convert rotational energy into upward thrust. The narrow blades simply lack the area to do this effectively. Pilots pushed engines to full RPM, fuel burned rapidly, temperatures rose, but the aircraft refused to climb with authority. German fighters exploited this weakness mercilessly. Alarm bells at Republic Aviation. In January 1943, at Republic Aviation's headquarters in Farmingdale, Long Island, senior engineers and executives began to recognize the severity of the issue. Among them was Alexander Kartveli, the Thunderbolt's chief designer. Combat reports from Europe painted a grim picture. German fighters dove through bomber formations, delivered their attacks, and then escaped vertically, knowing the Thunderbolt could not follow. Performance comparisons were damning. The W190A and Bf 109G reached combat altitude far faster than the P-47, giving the Luftwaffe both initiative and escape. These were not abstract statistics. Each shortfall translated into lost aircraft and dead pilots. Some commanders within the Army Air Forces began to question whether the Thunderbolt should even remain in frontline service. Kartveli, however, understood that the aircraft's flaws were not fundamental, they were mechanical and solvable. The key was propeller efficiency. Engineering the turning point. A propeller design is a delicate balance. Blade width, shape, weight, and pitch all influence how power is converted into thrust. Increasing blade area seemed like an obvious solution, but the risks were substantial. Wider blades could introduce dangerous vibrations. Improper mass distribution is capable of damaging the engine or airframe. Excessive torque could make aircraft unstable during takeoff or low-speed flight. Any redesign had to work seamlessly with existing Thunderbolts already deployed across multiple theaters of war. Throughout the brutal winter of 1943, engineers at American propeller manufacturers raced against time. While bomber crews continued to suffer losses over Germany, design teams tested new blade profiles that could harness the R-2800's power during climbs without compromising safety or reliability. The goal was simple in theory and complex in execution: create a propeller that could transform the Thunderbolt from a high-speed bruiser into a true high-altitude fighter. When the solution finally reached operational units, its impact was immediate and decisive. A shift in the air war. By March 1944, the P-47 Thunderbolt was no longer the aircraft German pilots believed they understood. The modification erased its most dangerous vulnerability and reshaped air combat over Europe. What had once been a reliable escape maneuver became a fatal mistake. The Thunderbolt had not changed its silhouette. Its engine had not grown more powerful. Yet a seemingly modest adjustment hidden in spinning metal at the nose altered the balance of power in the skies and helped pave the way toward air superiority over Germany. Sometimes the course of war turns not on strategy or heroism alone, but on the precise shape of a blade slicing through thin air at 28,000 feet. During the critical years of the Second World War, a seemingly technical engineering challenge evolved into a matter of life and death. Two American aerospace companies found themselves racing against time to solve a problem whose outcome would affect the fate of thousands of combat pilots. On one side stood Curtiss-Wright, long known for producing the original narrow-blade propellers. On the other was Hamilton Standard, a company with extensive experience supplying propellers for a wide range of U.S. military aircraft. Both firms clearly understood what was at stake. The winning solution would not only be produced in numbers well beyond 10,000 units, but more importantly, it would directly influence survival rates in aerial combat. By the winter of 1943, engineers at both companies were working relentlessly. Wind tunnel tests ran day and night, blade geometries were recalculated repeatedly. Stress tolerances were reanalyzed, and new hubs and pitch control systems were built and rebuilt. All the while, American pilots continued to fall in combat as designers debated fractions of inches in blade width and degrees of twist. Hamilton Standard's engineering team ultimately took a bold and unconventional path. Rather than refining the familiar thin knife-like blades designed to slice cleanly through air, they proposed something radically different. Their concept relied on broad, paddle-shaped blades that behaved less like cutting tools and more like oars driving through water. The blade chord was dramatically increased, and for much of its length the profile remained nearly rectangular, tapering only near the tip. To many engineers trained in classical aerodynamic theory, the design appeared inelegant, even crude. Yet, wind tunnel data told a different story. The wide blades delivered substantially higher thrust at low airspeeds while sacrificing very little in terms of maximum velocity. For aircraft that struggled during climb and acceleration, the implications were profound. Curtiss-Wright responded with its own wide blade solution, though it remained more faithful to traditional aerodynamic principles. Their propeller retained a smoother, elliptical outline while significantly expanding overall blade area. A notable feature of the Curtiss design was the addition of blade cuffs at the root, which helped guide airflow into the hub and reduced vibration during operation. Though stylistically different, both concepts represented a major leap forward compared to the narrow blade propellers then in service. In April 1943, Republic Aviation received prototype propellers from both manufacturers. Testing commenced immediately, both at Republic's own facilities and at Wright Field in Ohio. Test pilots conducted structured evaluations measuring climb rates, responsiveness, smoothness, and integration with existing aircraft systems. Results showed that both designs delivered dramatic improvements. Aircraft equipped with either propeller climbed far more effectively than before. Hamilton Standard's model provided slightly smoother handling, largely due to its hydraulic pitch control mechanism. Curtiss-Wright's propeller, however, integrated more easily with existing P-47 systems and proved simpler to retrofit onto aircraft already deployed overseas. Neither option dominated every performance category. Faced with this reality, the U.S. Army Air Forces chose practicality over prolonged debate. Rather than selecting a single winner, both designs were approved for production. Hamilton standard propellers would be installed on new P-47 seconds rolling off the production line at Republic's Farmingdale facility, beginning with the P-47 D-22 variant. Curtiss paddle blade propellers would be assigned to aircraft built at the Evansville, Indiana plant and distributed as retrofit kits for earlier Thunderbolts already operating in England. This dual-source approach accelerated deployment and had the added benefit of complicating enemy intelligence efforts. Production began in June 1943, but manufacturing challenges and testing delays pushed operational delivery back several months. The first combat-ready aircraft equipped with the new propellers did not arrive in England until late December. Throughout that month, P-47 seconds were ferried to RAF Wethersfield, where ground crews worked intensively to install the upgraded propellers. By early January 1944, the 56th Fighter Group, operating from Boxted in Essex, had completed its transition. The group's commander, Lieutenant Colonel Hubert Zemke, immediately grasped the tactical transformation these modifications enabled. The Thunderbolt's vastly improved climb performance allowed pilots to fight in the vertical, something that had been extremely dangerous with the earlier narrow-blade propellers. Zemke organized rigorous training throughout January, developing combat doctrines tailored specifically to the paddle blade-equipped P-47 seconds. Pilots learned to draw German fighters into climbing spirals, maneuvers that previously would have left the heavy Thunderbolt slow and exposed. New techniques emphasized converting speed into altitude, then diving back into combat with stored energy. Where earlier propellers would have caused the aircraft to struggle at low speed, the new blades turned these maneuvers into decisive offensive tools. By January 4, 1944, the transformation was no longer theoretical. The paddle blade Thunderbolt had reshaped how the aircraft fought and survived over Europe. When the 56th Fighter Group launched its first operational sortie with every aircraft fitted with the new paddle blade propeller, the effect was apparent almost immediately. Pilots reported a transformation so dramatic that it defied expectations for an aircraft weighing nearly 7 tons. The P-47 Thunderbolt, long criticized for its sluggish climb, now surged upward with an urgency previously thought unattainable for such a massive fighter. The most striking improvement appeared during vertical maneuvers. Where earlier Thunderbolts bled speed rapidly when climbing, the upgraded aircraft retained energy far more effectively. For the first time, American pilots found themselves able to pursue German fighters into steep upward escapes without surrendering altitude or tactical position. This shift would soon be tested under the harshest conditions deep inside enemy airspace over Germany. The new configuration entered combat during bomber escort missions in late January and early February of 1944. Almost immediately, American pilots encountered baffling reactions from their opponents. Luftwaffe fighter pilots attempted familiar disengagement techniques, high-speed dives followed by aggressive climbing turns, only to discover that the pursuing Thunderbolts remained locked onto their tails. In several encounters, German pilots assumed they were facing an entirely new American fighter design. This assumption collapsed when Luftwaffe intelligence officers reviewed gun camera footage. The film clearly showed standard P-47 Thunderbolts performing feats of vertical pursuit that had been impossible just weeks earlier. Confusion spread rapidly through German fighter units. The same aircraft they had outclimbed for months was now matching them step for step in the vertical plane. The situation reached a dramatic turning point on March 6, 1944. That day, Lieutenant Colonel Hubert Zemke led a formation of 48 Thunderbolts escorting heavy bombers toward Brunswick, a route that passed near Berlin itself. German air defense controllers responded by directing more than 80 Messerschmitt Bf 109 seconds and Focke-Wulf W 190 seconds to intercept the incoming force. As the bomber stream crossed into hostile airspace at approximately 24,000 feet, German fighters attacked according to established doctrine, diving through the bomber formations and then pulling sharply into steep climbs to escape the escorting fighters. For the first time, that tactic failed on a wide scale. Across the engagement, Thunderbolt pilots remained with the climbing German fighters, matching their ascent and maintaining firing positions. Veterans such as Captain Robert S. Johnson and Lieutenant Walker Bud Maharin engaged enemy aircraft in sustained vertical combat at high altitude and destroyed them during their escape attempts. By the end of the mission, the 56th Fighter Group claimed 11 aerial victories without losing a single P-47. Even more critically, every bomber under their protection returned safely. German pilots who survived the engagement reported unsettling observations after landing. American Thunderbolts, they insisted, had climbed alongside them. Several pilots again concluded that a previously unknown American fighter must have entered service. When intelligence officers presented gun camera evidence confirming that ordinary P-47 seconds were responsible, uncertainty within Luftwaffe units only deepened. Understanding the cause of this sudden shift became an urgent priority. An early clue had already emerged weeks earlier. In early February, a downed P-47D-23 was recovered and transported to the Luftwaffe test center at Rechlin. Engineers inspecting the wreckage immediately noticed an unfamiliar feature. The propeller blades were significantly wider than those seen on earlier Thunderbolt variants. Technical reports described the new propeller design in detail but initially underestimated its importance. Analysts concluded that the modification was likely intended to improve takeoff performance rather than alter combat capability. This misjudgment proved costly. Throughout February 1944, increasing numbers of P-47 units converted to the paddle blade propeller. The 4th Fighter Group completed its transition in early February, followed by the 78th Fighter Group by mid-month. By the end of February, 6 of the 8th Thunderbolt groups stationed in England were operating aircraft equipped with the new propeller. Each unit reported immediate and measurable gains in combat performance. As these upgrades spread, German losses mounted. Luftwaffe pilots found that escape maneuvers which had reliably saved their lives for over a year were now leading them directly into American gunfire. On February 21, 1944, Jagdgeschwader 26 suffered the loss of 7 February 190 seconds in a single encounter with the 56th Fighter Group. The unit's commander, Major Klaus Meitisch, submitted an after-action report that reflected mounting frustration. His pilots, he explained, had followed approved tactical doctrine, engaging briefly and disengaging through climbing maneuvers when pressured. Every pilot who attempted this escape method was shot down. Meitisch urgently requested clarification on whether the United States had fielded a new fighter and whether existing Luftwaffe doctrine was still viable. At the time, German intelligence had no clear answer. Gradually, through further wreckage analysis and battlefield observation, the picture became clearer. By March 1944, Luftwaffe analysts recognized that American engineers had fundamentally altered the Thunderbolt's performance by redesigning its propeller. The new paddle blade configuration generated far greater thrust at low airspeeds, particularly during climbs, transforming the aircraft's vertical combat ability. Warnings circulated through Luftwaffe channels advising pilots that American fighters could now contest vertical engagements. New recommendations emphasized attacking only from a position of clear energy advantage and disengaging through level, high-speed flight rather than upward escape. Yet implementing such changes across hundreds of squadrons proved nearly impossible. Pilots who had survived for months by instinctively climbing away could not instantly override deeply ingrained habits. The full scale of the transformation became unmistakable during Big Week, the massive Allied bombing offensive against German aircraft production facilities in late February 1944. By then, the Thunderbolt was no longer merely a rugged escort fighter. It had become a vertical combat threat that permanently altered the balance of air combat over Europe. Between February 20 and February 25, the air war over Europe reached a decisive turning point. During these 6 days, the U.S. 8th Air Force committed enormous resources to sustained strategic bombing operations. More than 3,800 heavy bomber missions were flown deep into German-controlled territory, shielded by over 3,600 fighter escort sorties. By this stage of the war, the backbone of American fighter protection was no longer a mix of aircraft types. The overwhelming majority were P-47 Thunderbolts fitted with wide, paddle-shaped propellers. The German response was massive but increasingly costly. The Luftwaffe launched more than 2,000 defensive sorties, attempting to intercept and disrupt the bomber streams, yet the results revealed a dramatic imbalance. German units suffered catastrophic losses. Approximately 355 fighters were destroyed outright, with an additional 100 aircraft so badly damaged that they were written off. In contrast, American fighter losses amounted to just 28 aircraft. The air combat exchange rate had shifted decisively, signaling a collapse of German air parity. This shift was not the result of a single revolutionary technology, but rather the refinement of an existing aircraft pushed closer to its full potential. Thunderbolt pilots quickly learned that the new paddle blade propellers offered advantages far beyond improved climb rates. The broader blades generated significantly greater thrust at lower airspeeds, allowing P-47 seconds to regain energy more rapidly after high-speed dives. What had once been a heavy aircraft reliant on straight-line speed became a platform capable of repeated dive and climb attack cycles, keeping constant pressure on enemy fighters throughout prolonged engagements. The increased thrust also reshaped how the Thunderbolt handled at the margins of performance. Although it still could not match the Bf-109 or FAVU-190 in tight level turns, the P-47 no longer needed to compete in that regime. Instead, pilots discovered they could preserve enough energy in ascending turns to deny German fighters the angular advantage they normally sought. This allowed American pilots to fight vertically rather than horizontally, an approach better suited to the Thunderbolt's strengths. No pilot exploited this change more effectively than Major Francis Gaby Gabreski, commander of the 61st Fighter Squadron within the famed 56th Fighter Group. Gabreski became the strongest advocate of a tactic the pilots informally called the climbing spiral. His method began with engagement at equal altitude, typically around 24,000 feet. Rather than tightening into a flat turn, Gabreski would retain speed and pull the Thunderbolt into a gradual climbing arc. German pilots, accustomed to seeing earlier model P-47 seconds bleed energy in such maneuvers, often followed. They expected the heavier American fighter to slow, stall, or present an opening. Instead, the paddle blade-equipped Thunderbolt continued climbing even while turning. Gabreski would maintain the maneuver through 2 or 3 full upward spirals, steadily draining the German fighter's energy reserves. Eventually, the pursuing aircraft would either stall outright or be forced to disengage. At that critical moment, Gabreski reversed direction. With the enemy fighter now slow, high, and vulnerable, the Thunderbolt plunged downward, converting altitude into speed. The German pilot, deprived of both energy and escape options, was left exposed. Gabreski would close rapidly and fire from a position of overwhelming advantage. By the end of his combat career, Gabreski had claimed 28 aerial victories, all while flying the P-47. This made him the highest-scoring American ace in the European theater who achieved all of his victories in a single aircraft type. Notably, nearly all of those kills came after his unit transitioned to paddle blade propellers. In interviews after the war, Gabreski repeatedly emphasized that no other modification had transformed the Thunderbolts as profoundly. In his view, the propeller upgrade was the single most important factor in turning the P-47 into a dominant air combat machine. Crucially, this transformation did not demand extensive changes in pilot doctrine or training. There was no need for elaborate retraining programs or new combat manuals. The aircraft simply responded more faithfully to pilot inputs, retaining energy in situations where earlier versions would have fallen short. The Thunderbolt did what pilots asked of it and did so consistently. The paddle blade propeller program stands as a case study in American industrial coordination under wartime pressure. From the moment the concept was identified to its widespread frontline deployment, the entire process took approximately 9 months. two separate manufacturers independently designed and tested competing propeller solutions. Republic Aviation adjusted production workflows at two major factories. The USI Army Air Forces simultaneously revised maintenance procedures, trained ground crews, and transported thousands of finished propellers across the Atlantic. None of these steps were individually groundbreaking. The true achievement was the speed, scale, and synchronization with which they were executed. Germany recognized the same aerodynamic shortcomings. Engineers at Messerschmitt and Focke-Wulf fully understood the theoretical advantages of increased propeller blade area. They possessed the technical expertise to implement similar improvements. What they lacked was the strategic freedom to do so. By 1944, the German war economy was operating at absolute capacity, focused on producing existing fighter designs in sufficient numbers to offset devastating losses. Any major modification, such as a new propeller, would have required halting production lines, retooling factories, recalculating flight performance, revising maintenance documentation, and retraining mechanics. Even a temporary disruption would have meant thousands fewer fighters delivered at a time when Germany could not afford to lose a single aircraft. The Luftwaffe found itself trapped by circumstance, aware of the need to adapt, yet unable to absorb the cost of adaptation. This contrast revealed a deeper divergence between the two air powers. The United States possessed the industrial flexibility to identify weaknesses and correct them rapidly, even in the midst of full-scale production. Germany, constrained by strategic desperation and limited industrial margin, could innovate in theory but not in practice. The paddle blade propeller did not merely improve the P-47. It exposed the growing structural imbalance that would ultimately decide control of the skies over Europe. American aircraft engineers during the Second World War tended to favor solutions that could be deployed rapidly, even if those solutions were not theoretically ideal. Rather than pursuing years of refinement to achieve perfect aerodynamic efficiency, they often accepted designs that were good enough to meet urgent operational needs. The paddle blade propeller was a clear example of this philosophy in practice. From a purely aerodynamic standpoint, the wide-chord paddle blade propeller was inferior to slimmer, more refined blade designs. At higher speeds, its bronze surfaces generated increased drag, reducing efficiency compared to narrow blade propellers. The design also added weight, forcing engineers to reinforce the propeller hub and strengthen pitch control systems. Yet despite these drawbacks, the paddle blade configuration delivered an immediate and decisive benefit. It dramatically improved low-speed thrust without requiring prolonged development or complex optimization. German engineers, by contrast, frequently pursued theoretical excellence even when practical implementation lagged behind. Propeller designers in Germany invested considerable effort into advanced variable pitch systems that promised superior performance on paper. However, many of these sophisticated designs never progressed beyond prototypes or engineering drawings. They failed to appear in operational squadrons in numbers sufficient to influence the air war. By early 1944, this divergence in design philosophy began to produce tangible results. By March of that year, the P-47 Thunderbolt, equipped with paddle blade propellers, had become the primary long-range escort fighter for American bomber formations over Europe. The aircraft was no longer a stopgap solution waiting to be replaced by the P-51 Mustang. Instead, it had matured into a highly capable fighter in its own right. With its upgraded propeller, the Thunderbolt evolved from a compromised high-altitude interceptor into a dominant air superiority platform. In most combat scenarios, it could now challenge and often defeat its German adversaries. This transformation had profound psychological consequences on both sides of the conflict. Throughout much of 1943, American bomber crews had watched German fighters climb effortlessly out of danger after brief engagements. By 1944, that dynamic had reversed. German aircraft attempting to disengage using vertical maneuvers were now pursued, overtaken, and destroyed. Luftwaffe pilots, already strained by growing American numerical strength, found that many of their traditional tactical advantages had vanished. The Focke-Wulf 190, an aircraft engineered to outperform the Thunderbolt in nearly every measured parameter, discovered that its edge had been neutralized in the one domain where it still held superiority. Likewise, the Messerschmitt Bf 109 could no longer depend on rapid climbs to escape combat. The result was a steady increase in German fighter losses as the spring of 1944 progressed. Experienced Luftwaffe pilots, men who had survived years of combat, were increasingly shot down by Thunderbolts they believed they had successfully shaken off. The consequences of this shift became unmistakable during the build-up to the Allied invasion of Western Europe. In May 1944, American fighter units launched sustained operations to secure air dominance over France. Thunderbolts swept across northern regions, strafing airfields, destroying aircraft on the ground, and engaging any German fighters that attempted to intervene. P-47 seconds equipped with paddle blade propellers proved especially lethal during these missions. German interceptors were often forced to scramble from lower altitudes to challenge American fighters operating between 20,000 and 25,000 feet. In these encounters, Thunderbolts could dive onto climbing opponents, strike decisively, and then climb back to safety before the Germans could mount an effective counterattack. On June 6, 1944, as Allied troops landed on the beaches of Normandy, Thunderbolts maintained constant air cover throughout the day. German fighters attempting to attack the invasion fleet or support ground forces were repeatedly intercepted and destroyed by paddle blade-equipped P-47 seconds. The imbalance was stark. During the critical first 24 hours of the invasion, the Luftwaffe managed fewer than 100 sorties over the beaches. In the same period, American fighters flew more than 8,700 missions. This overwhelming dominance was sustained by kill ratios of 4-to-1 or higher. By eliminating the Thunderbolt's most significant weakness, its relatively poor climb performance, the paddle blade propeller played a direct role in achieving the air superiority that made the invasion possible. Pilot testimonies were reinforced by statistical data. In the first quarter of 1944, before paddle blade propellers became common, American fighters in Europe achieved an average kill ratio of roughly 1.8-to-1. By the second quarter, as paddle blade installations became widespread, that figure rose to approximately 3.2-to-1. By the third quarter of the year, the ratio had increased further, reaching 4.6-to-1. These gains cannot be attributed solely to the propeller upgrade. American forces enjoyed growing numerical advantages, pilot training improved steadily, and Germany increasingly relied on inexperienced replacements to offset mounting losses. Nevertheless, combat reports consistently emphasized the importance of improved climb performance in securing these victories. The most widely deployed version of the new propeller, the Curtiss Electric C542s, featured 4 blades spanning a diameter of 13 feet. Each blade possessed a substantially larger surface area than earlier narrow blade models. This dramatic increase in blade area translated directly into significantly greater thrust at low airspeeds, an advantage that reshaped air combat over Europe in the final year of the war. By the later stages of P-47 Thunderbolt production, a new propeller configuration had become standard equipment. The Hamilton Standard paddle blade propeller, introduced on subsequent variants, delivered flight performance comparable to earlier designs while offering clear advantages in day-to-day operations. Unlike the Curtiss Electric system, which relied on electrically driven pitch adjustment, the Hamilton Standard unit used a hydraulically actuated pitch mechanism. This approach proved both mechanically simpler and more dependable under combat conditions. Despite differences in internal systems, the overall blade surface area remained virtually unchanged, and pilots reported no noticeable distinction in combat effectiveness between the two designs. Outfitting the entire Thunderbolt fleet with these propellers became a powerful illustration of the scale and efficiency of American wartime industry. Between mid-1943 and the end of 1944, production lines operated by Curtiss-Wright and Hamilton Standard delivered many thousands of complete propeller units. Each assembly was a complex system composed of 4 broad blades, a central hub, a pitch control mechanism, and specialized mounting components engineered to withstand extreme stresses. The blades themselves were manufactured through an intensive process. Aluminum alloy billets were first forged, then precision machined into carefully calculated airfoil profiles. Following machining, each blade underwent heat treatment to ensure optimal strength and durability. From raw forging to finished component, a single blade demanded roughly 14 hours of machine time, not counting preparatory work or surface finishing. Once completed, the challenge shifted from production to delivery. Transporting these massive propeller assemblies to operational squadrons stationed in the United Kingdom was no simple task. Each unit weighed close to 650 pounds and required meticulous handling to avoid warping or surface damage. For transatlantic shipment, propellers were secured inside reinforced wooden crates fitted with internal bracing. These crates were loaded aboard cargo ships bound for Europe, with crossings that typically lasted around 2 weeks. After arriving at British ports, the propellers were transferred to air depot facilities where maintenance crews prepared them for installation. Replacing an existing propeller was a labor-intensive operation, taking approximately 16 hours per aircraft. The process included removing the old unit, fitting the new assembly, carefully aligning and calibrating the pitch control system, and conducting thorough ground tests before the aircraft was cleared for flight. Despite these demands, depot personnel achieved remarkable results. Between January and June of 1944 alone, more than 1,000 Thunderbolts were upgraded in England without disrupting the combat readiness of frontline fighter groups. As these improved aircraft entered service, combat tactics continued to evolve. Through the summer and autumn of 1944, P-47 pilots refined new methods to take full advantage of the enhanced climb performance provided by the paddle blade propeller. One particularly successful maneuver was a coordinated vertical engagement involving 2 Thunderbolts working as a team. In this tactic, a German fighter attempting to climb away from one P-47 would unknowingly expose itself to the second aircraft, which positioned for an attack at the moment the enemy aircraft began to lose energy. The opposing pilot faced a no-win decision: continue climbing until the aircraft stalled and become vulnerable, or abandon the climb to preserve speed only to be met by a high-speed diving attack from the lead Thunderbolt. At the same time, the role of the paddle blade Thunderbolt expanded beyond air-to-air combat. These aircraft increasingly proved their value at low altitudes, where they were used extensively for ground attack missions. The combination of durability, firepower, and improved propeller efficiency made the upgraded P-47 a formidable presence not only in the skies above Europe but also over the battlefields below. The introduction of paddle blade propellers fundamentally changed how the P-47 Thunderbolt performed in combat, particularly at lower speeds and under heavy load. Aircraft that once struggled to retain energy when burdened with bombs or rockets could now fly faster, climb more efficiently, and maneuver with greater confidence. Even when carrying up to 2,500 pounds of external ordnance, upgraded Thunderbolts maintained the speed necessary to survive over hostile territory. This improvement had immediate tactical consequences. Pilots attacking German ground positions were no longer forced to begin their dive attacks from high altitude. Instead, they could initiate strikes closer to the ground, shortening the time spent exposed to anti-aircraft fire. Once weapons were released, the enhanced thrust produced by the wider propeller blades allowed the aircraft to pull away quickly, reducing vulnerability during the most dangerous phase of the mission. The results were measurable. From April through September 1944 alone, Thunderbolt units carried out more than 88,000 ground attack missions. During this intense operational period, losses totaled roughly 820 aircraft from all causes, representing a loss rate of under 1%, an extraordinary figure given the nature of low-altitude combat. As newer fighters with greater range, particularly the P-51 Mustang, entered service, many expected the Thunderbolt to be gradually replaced. Instead, the opposite occurred in several frontline units. Thanks to the performance gains delivered by the paddle blade propeller, the P-47 proved adaptable enough to remain a first-line aircraft. Fighter groups valued its ability to perform escort duties, air combat, and ground attack with equal effectiveness. One of the most notable examples was the 56th Fighter Group. Under the leadership of Colonel Hubert Zemke and later Colonel David Schilling, the unit flew Thunderbolts exclusively for the entire duration of the war. Although opportunities existed to convert to Mustangs, the group declined. Its pilots trusted the Thunderbolt's rugged airframe, heavy 8-gun armament, and improved climb rate features they believed better suited their operational needs than the lighter Mustang. Enemy pilots took notice as well. German aviators who survived the conflict frequently cited the paddle-blade Thunderbolt as one of the most formidable American fighters they encountered. Major Gunter Roll, credited with 275 aerial victories, remarked after the war that later Thunderbolt variants were far more dangerous than earlier models. He emphasized that German pilots learned to treat these upgraded P-47 seconds with the same caution they reserved for P-51 seconds, recognizing that the American aircraft could now compete effectively in most combat scenarios. Beyond battlefield performance, the program offered valuable lessons for aircraft development. The success of the paddle-blade propeller demonstrated that meaningful gains could often be achieved through targeted upgrades rather than entirely new designs. The Thunderbolt itself continued to evolve, benefiting from additional enhancements beyond its propeller system. One such improvement was the adoption of water methanol injection, which temporarily boosted engine output to approximately 2,535 horsepower. When combined with the increased thrust efficiency of paddle blade propellers, this system delivered dramatic performance gains. The P-47M, introduced toward the end of 1944, integrated both features and achieved climb rates that rivaled or surpassed those of contemporary German fighters. Financially, the program was remarkably efficient. The combined development costs for the Curtiss and Hamilton standard paddle blade propellers, including wind tunnel research, prototype manufacturing, and flight testing, amounted to roughly $3 million. In contrast, designing an entirely new fighter aircraft would have required investments exceeding $100 million and several years before reaching operational readiness. In this sense, the paddle blade propeller embodied the pragmatic approach that characterized much of American wartime production. It also underscored the importance of rapid feedback between combat units and engineers. Frontline pilots were the first to identify the shortcomings of narrow-blade propellers, reporting situations in which German fighters escaped by climbing away. These observations moved through intelligence and technical channels, enabling engineers to pinpoint the problem and implement solutions within months. While similar feedback mechanisms existed in Germany, they became increasingly ineffective as the war progressed and the nation's strategic situation deteriorated. In contrast, the Allied system remained responsive and flexible, allowing improvements to be fielded quickly and at scale. The broader consequences extended beyond aerial combat. The establishment of air superiority over Western Europe, supported in large part by improved Thunderbolt units, gave Allied ground forces freedom of movement. During the breakout from Normandy in August 1944, American troops advanced under a protective canopy of air power, maintained to a significant degree by Thunderbolts operating relentlessly overhead. In the end, the paddle blade propeller was more than a mechanical upgrade. It was a force multiplier, one that helped ensure Allied dominance in the air and accelerated the collapse of German resistance on the ground. As Allied armies pushed deeper into occupied Europe, German ground units attempting to withdraw, regroup, or establish new defensive lines increasingly found themselves exposed from the air. Allied fighter bombers dominated the skies, striking columns of vehicles, armor, and infantry with relentless precision. Any attempt by German fighter aircraft to disrupt these attacks faced a new and unforgiving reality. Escorting P-47 Thunderbolts, now significantly improved, could intercept and eliminate enemy aircraft before they posed a serious threat. The transformation of the Thunderbolt into a more capable vertical fighter changed the balance of tactical air combat. German interceptors that tried to challenge Allied ground attack missions were often met by P-47 seconds that could climb faster and respond more aggressively than earlier versions of the aircraft allowed. This shift sharply reduced the Luftwaffe's ability to protect its own forces on the battlefield. The last major air engagements involving large formations of paddle-blade-equipped Thunderbolts took place during the Battle of the Bulge in the winter of 1944-1945. When German forces launched their surprise offensive through the Ardennes in December 1944, heavy cloud cover and poor weather initially grounded much of the Allied air power, allowing the attack to gain momentum. For several days, German troops advanced largely unchallenged from above. That advantage vanished on December 23, when weather conditions finally improved. Allied air forces responded immediately with overwhelming force. Fighter bombers flooded the skies, targeting German supply routes, armored spearheads, artillery positions, and transport columns. Thunderbolts fitted with paddle blade propellers flew mission after mission, sometimes several per aircraft per day, delivering sustained punishment across the battlefield. German fighters attempted to intervene, but their efforts rarely succeeded. Escorting P-47 seconds consistently drove them away, often destroying attackers before they could disrupt the strikes. By early 1945, this pattern had become the norm rather than the exception. By February of that year, organized Luftwaffe resistance over Western Europe had largely collapsed. Surviving German fighter units were pulled back to defend the Reich itself against the intensifying Allied strategic bombing campaign. While many factors contributed to this outcome, the upgraded Thunderbolt played a meaningful role in achieving the air superiority that made further Allied advances possible. Despite this, the Thunderbolt's contribution has often been overshadowed by the more celebrated P-51 Mustang. Historians frequently point out that Mustangs claimed higher numbers of aerial victories and escorted bombers deep into German territory. While these points are accurate, they do not tell the full story. Between January and December 1944, Thunderbolt units were credited with destroying approximately 3,800 German aircraft in air-to-air combat, while losing around 820. This resulted in an overall kill ratio of roughly 3.7 to 1, a figure comparable to or better than many other American fighters operating during the same period. More importantly, the Thunderbolt's improvement came at a time when German fighter forces remained dangerous and capable. The aircraft's evolution from a sluggish climber into a reliable vertical combatant occurred precisely when such performance was most urgently required. The post-war fate of the paddle-blade Thunderbolt illustrates how quickly even effective wartime innovations can fade from memory. With the arrival of jet-powered fighters, piston-engine aircraft like the P-47 rapidly became outdated. Most surviving Thunderbolts were scrapped or sold abroad, and the engineering advances that had enhanced their combat performance were soon eclipsed by the dramatic promise of jet propulsion. Few pilots who flew the improved Thunderbolts later held positions that allowed them to shape its historical legacy. Yet the paddle blade propeller represents a form of military innovation that deserves greater recognition. It was not a dramatic technological leap that redefined aerial warfare overnight. Instead, it was a carefully engineered refinement that addressed a specific weakness in an existing design and did so with remarkable effectiveness. This kind of evolutionary improvement, rather than revolutionary invention, characterized much of America's wartime success. The underlying engineering principles remain relevant even today. The lesson that blade surface area must be optimized for real-world operating conditions, not theoretical peak efficiency, applies directly to modern turbine engines, helicopter rotors, and unmanned aerial vehicle propulsion systems. Engineers continue to face the challenge of balancing competing performance demands across different flight regimes, just as their wartime predecessors did. From the German perspective, the success of the paddle-blade Thunderbolt highlights the consequences of strategic and industrial decline. German engineers fully understood propeller theory and were technically capable of producing similar improvements. What they lacked was time, material, and an industrial system resilient enough to support rapid development and large-scale implementation under constant bombardment. The Thunderbolt's success was not the result of superior intellect alone, but of an industrial structure capable of identifying problems, developing practical solutions, and deploying them quickly and widely. Wars are rarely decided by single wonder weapons or revolutionary breakthroughs. They are won through the cumulative impact of countless incremental advances, each addressing a specific limitation, each reinforcing overall effectiveness. The paddle blade propeller was one such improvement, modest in appearance but decisive in effect. By eliminating the Thunderbolt's most serious flaw at a critical stage of the war, it helped secure air dominance over Europe, supported the success of the Allied invasion, and hastened Germany's defeat. Though born from the quiet work of engineers rather than dramatic dogfights, its contribution stands as one of the understated technological achievements of the Allied victory.